Welcome to today's IEAGHG webinar on the recent study, Prospective Integration of Geothermal Energy with Carbon Capture and Storage. My name is Nicola Clarke, and I'll be your presenter today. I'm a Senior Technology Analyst at IEAGHG, and I'm very pleased to welcome you to today's webinar. Just a short disclaimer slide that we show at the beginning of all our presentations. The IEAGHG is organised under the IEA, but is functionally and legally autonomous, and the views, findings and publications of the IEAGHG do not necessarily represent the views or policies of the IEA Secretariat or its individual member countries. I will begin this webinar by the short overview of IEAGHG, followed by a brief background and motivation of the study. We'll then be joined by my co-presenter and his team, Christophe Kervevan, who will give us a comprehensive overview of the work undertaken by BRGM. We'll then have time for questions at the end, and please type the questions into the question box and I'll collate them at the end of the session. The IEAGHG is a collaborative international research programme founded under the IEA in 1991. The aim is to provide information on the role that technology can play in reducing greenhouse gas emissions from use of fossil fuels and biomass in power and industrial systems. The main focus is on carbon dioxide capture and storage, CCS, and we produce information that's objective, trustworthy and independent, policy relevant but not policy prescriptive, and is reviewed by external expert reviewers. IEA is a members-based organisation, and thanks to their support, we can fund our research activities. We currently have 36 members comprising countries, companies and organisations, and our members steer the direction of our studies. IEAGHG helps facilitate knowledge sharing through a number of pathways, through external involvement with the organisations shown on this slide and through the programme's main activities. These are funding research into development and deployment of CCS technologies. We produce technical reports which can be found on our website, which publish on all aspects of CCUS. We also host a number of expert networks, of which the following have had meetings this year: the Risk Management Network, Monitoring, High Temperature Solid Looping and Costs. And there'll be shortly some reports on these meetings on our website. We also host a number of conferences, the GHG series, of which I'll mention in a moment, the Post-Carbon Combustion Capture Conference, of which is being held in Pittsburgh right now, the Negative CO2 Emissions Conference, which will be held next summer in Oxford, and we also host an international CCS summer schools, which hold every year. GHGT is the largest international conference for the CCUS community, and the 17th in the series will take place next year in Calgary. It's being hosted by the Emissions Reduction Alberta, and the call for abstracts is now open. You'll be welcome to register, and there's information to be held on the GHGT website. Just a quick note for the webinar procedures for today. As attendees, your mics will be muted throughout. If you have a question for our speakers, please type the question into the questions box in your control panel, as indicated on the right. We'll try and get through as many questions as possible, and we should have time for those at the end. And also please note that this webinar is being recorded, and a copy of it will be available on our YouTube channel shortly after the event. Just a bit of background to this study today. The dual challenge of the present energy and climate crisis offers opportunities for new ways of thinking, and there's been a resurgence of interest in geothermal energy combined with a maturing carbon capture and storage technologies, which offers a compelling argument to integrate subsurface and near-surface technologies where possible. So the aim of this study is to provide a dispassionate review and overview of different geothermal energy concepts for CO2 utilisation and storage technologies, and where there may be a potential for combining the two for mutual benefit. So we've just published a report on this. It was published in August to our members and will be publicly available from February. The contractor was BRGM, of which I'm glad to say we have the full team with us today. And let me introduce them to you now. So we have Christophe Kervevan, Annick, Loschetter, Rowena Stead, Thomas Legonion, and Chrystel Dezayes. Sorry if I've mispronounced your names. Anyway, you can see them in the chat now. So I'm now going to hand over to Christophe, who's going to present the details of the study, and at the end, all of the members of the team will be available to your questions. So without further ado, I will change to Christophe.
Okay.
And
thank you.
Well,
thank you, Vicky. So just tell me if you can see my screen. Not.
No, it's okay. We see your screen.
Okay. But I don't see my screen now. Okay, thank you for this introduction. And so I'm Christophe Kervevan from BRGM, and beside me there is a part of the team in this room, and the rest of the team is online, connected today, and ready to answer your questions at the end of this presentation. So I would like to insist on the fact that it's really teamwork, and today I have the responsibility to present most of the results of this study, but I'm just talking on behalf of the whole teams. Okay, so a short introduction first. The objectives of the study were clearly defined by IEAGHG, and we had to answer three main questions. The first one was what type of hybrid CCS geothermal system are either operational or described in the literature. The second question was more on the main criteria that should be considered to enable comparison between those systems. And the third question was on the region that tried to identify the region that had the most favorable features for future implementation of these technologies. So the program was very dense, as you can see. So first, let's start by the literature review. So first of all, I would like to apologize because we've made the choice to go through all the concepts identified through this literature review, which means that I won't have time to spend a lot of time on each of the concepts. So and for that reason, we of course warmly encourage you to read the report to have all the detail you would like to see on this concept. So first of all, because there were a lot of concepts and most of them were pretty close to each other at first sight, so it was really indispensable to propose a classification for this concept. So that was what we've made. We have a first category of concept that use supercritical CO2 as a heat vector instead of water for geothermal exploitation, and for some of them for energy storage. So that's category number one. Then we have category number two with two subcategories. It's basically a water-driven geothermal heat extraction and CO2 injection, as well as being dissolved in the water with two different objectives, as we will see later. And then we have this third category with other synergies that could be identified from with geothermal fluid and CO2 for CCS, which are handled separately as a difference with the previous categories. And we have a last category that I just mentioned, but I'm not going to talk about it today because it's some sort of really borderline concepts which are basically out of scope of this study. In order to understand and identify more clearly those concepts, we have represented those concepts through infographics, for which we really use this, of course, the same symbols. So there is a legend that you should have in mind. So not today, but in the report, of course. And also we had to compare what we call the services offered by each of the concepts. Basically, in terms of CCS, energy production, and sometimes energy storage. So to compare those we needed to put numbers, and we decided to use that type of numbers. So I don't have time to enter into too much details about that, but keep in mind that we have based those numbers on the cost for electricity from IEA, so really from the real data, and we have tried to put some those numbers on the defining specific ratios for CCS and electricity or thermal energy production. So let's go through the first category of concept. So just to mention how we have represented those concepts. So the first one is CPG, that many of you probably already have heard about. It's the CO2 plume geothermal. So in every slide that is going to come after this one, you will see in the middle a little sketch representing basically the way things work. Here you have the two wells, and below you have a short text giving some more details about it. And on the left, you will see some key numbers and some, let's say, some sort of pros and cons of the concept, and something that is named TRL, where we present different things that have been done for this specific concept. And on the right, you will see some numbers, so quantitative data about the services provided using the methodology presented previously. Okay, so in this CPG, so the idea really is to use like every other of these categories, CO2 as the heat vector for geothermal energy, and at the same time you will have some part of the CO2 that will remain stored in the reservoir. So it is a CCS technology as well. So CO2 storage is not the primary objective. The primary objective is to produce as much energy as possible. But you can see here that you can expect storing a few tens of million tons of CO2 over a lifetime of the system that we estimated to be about 30 years. But the same monitoring technology are necessary as standard CCS, and but of course it requires high investment, as you can see. So we are talking about sedimentary and porous reservoir, but we need a period of initialization so that the CO2 plume reaches the production wells, and this takes several months at least, and it could take years. So during this period, there is no energy productions, just CCS only. So this is something to be kept in mind. So let's go to next, which is CO2 EGS. So the major difference is here that we are in fractured reservoirs, so it's an enhanced geothermal system that you probably already know as well. So of course, in this case, we are much deeper than in the first case. The temperature is higher and the energy production is higher, but the amount of CO2 being possibly stored is lower. And of course, there are some new risks with respect to the previous one, because we have this stimulation which is needed to activate some fractures, and and of course it can lead to some potential issues. So let's go to the next one, which is heat mining with supercritical CO2 in depleted oil and gas reservoir. So this basically is a revisited version of EOR and EGR, where the authors want to produce, to co-produce geothermal energy, and using as well supercritical CO2 as heat vector. But also they plan to use non-condensable gases, just like methane, for example, that could be in the reservoir to produce some more energy. So that's one of the difference with respect to the previous case. And so we have about the same depth as the previous case, but higher temperature, but lower energy and lower CO2 storage. But yeah, so let's go to the next one, which is CPG ES. So ES means energy storage, or F, sometimes called F for flexible. So this is a CPG system in which there is a main difference, which is the fact that they plan to use two reservoirs, one deep reservoir, just like in standard CPG, and a supplementary reservoir, which is a shallower reservoir that will be used for reversible storage of CO2, depending on the demand on electricity. So of course, the idea is to reduce the parasitic load due to injection of CO2 in the deep aquifer. So sometimes when there is need for more electricity, we use less electricity to store in the shallower reservoir. And with that option, we have a new possibility, which is some energy storage in this reservoir. So this is a new option that is offered by this concept. And it's a lot of engineering for this to work, because there is need for concentric layout of the wells. So I'm not entering into details, but it's at least 6 wells and 2 aquifers, so which means that it's a bit complex to set up. Okay, so there is less depth and less high temperature, but less energy, but more CO2 storage potentially that could be stored by this concept. And the last one is what is called Earth Battery, or BES for bulk energy storage. So this is a system that combines brine and supercritical CO2 geothermal energy exploitation, CO2 storage, bulk energy storage with a CO2 pressurized cushion gas. So basically, what you have is that you have a complex system of well rings with concentric layout, and part of the CO2 and the water, which is used for geothermal production of geothermal energy, is injected and produced through a different well. First, in the middle, is used for production well of high pressure CO2, and the high pressure is obtained through lateral injection of water that is going to avoid the extension of the water bubble, then to increase the pressure. So it's a bit complex, but there is also the possibility to provide the service of energy storage in this system. And there is necessity to use high depth and high temperatures, but of course the anticipated production of energy is very high, and the anticipated CO2 storage possibility is very high as well. So it's a system that should bring very high performance, but as you can see, and as you can guess, because you don't see all the complexity, because this is a very simplified sketch. If you look at the publication of the paper, the original paper, it's much more complex than this. So it's a complex system, but with potential very high performance. And we have this system of retrieving water temporary and storing temporary at the surface. So we need a reservoir. So it's very complex. Let's skip to the next category, which is the water-driven geothermal heat extraction. So, and the objective is here to use actually to use CCS to decarbonize geothermal energy production. So the first concept we wanted to mention is the CARFIX concept. CARFIX basically is a CCS option, but in the first pilots in Iceland, they've used it combined with geothermal energy production, and the idea was to reinject CO2 and also H2S co-produced by the geothermal fluid, so that the global geothermal performance is less CO2 emitting. And so the CO2 storage was not the primary objective because it was basically a geothermal plant, but the idea was to decarbonize and taking benefit of the geological context with the presence of mafic and ultramafic rock, which permit when CO2 is injected as being entirely dissolved in water to trigger some geochemical reaction that very quickly, in a couple of years, transform dissolved CO2 to minerals. So, which is the ultimate form of storage. So there is all these elements, this specific geology and the geothermal power plant. And so as you can see, the ratio, the comparative ratio of CCS and geothermal energy is greatly in favor of energy production. In this case, the amount of CO2 avoided is small compared to the amount of energy produced. And now we have a second concept, which is called CO2 reinjection. So here in several places in the world, the geothermal fluid contains non-condensable gases, just like methane and CO2. And here particularly CO2, and the idea is to reinject this CO2 to have at the end a near zero emission geothermal energy. For example, in test cases in Turkey or Italy, there are really a great concentration of dissolved CO2 in the geothermal fluid, so it is important to decrease this CO2 emission. Of course, if this CO2 is vented to the atmosphere, it's not very satisfying on an environmental point of view. So here the CO2 can be reinjected as being dissolved in water or partly as a supercritical phase. So we still have a geothermal power plant, of course, here, and two options of CO2 storage. So here the depth is higher than in the CARFIX example. The temperatures are about the same, but the energy production is lower or equivalent. It really depends on the cases, but the amount of CO2 potentially that could be potentially stored is relatively high, as you can see. Another interesting concept is what we call the IEAGHG. So not an easy name, but it's basically the name of the company, IEAGHG, who created the concept, and IEAGG is a subsidiary operating in Croatia, where there is a first pilot operating or about to operate in the few months to come. So here the idea is to really fully utilize the whole potential of the hot brines. We use the heat. So we're still in a hydrothermal reservoir, but with brine containing both CO2 and CH4. And the geothermal power plant is producing both electricity and heat. So the interesting thing is that the methane will be exploited to produce electricity through a gas turbine. And then the CO2 emitted by this gas turbine when burning CH4 is going also to be reinjected in the reservoir, so that at the end we have a near zero emission system producing electricity and heat, because of course the hot brine is used also to produce electricity with combined with an ORC system, and the remaining heat is used to feed a nearby heating network. So the depth is about 2 kilometers in this site in Croatia. The temperature is between 100 and 120 degrees C, so relatively low compared to the previous examples. So of course the amount of energy produced is going to be a bit lower, but it's still significant in both electric and thermal energy. And the avoided amount of CO2 is smaller than the other cases, but it's not negligible. It's about 2 million tons over 30 years of operation. So now if we skip to the next category, which is water-driven geothermal heat extraction, still with injection of CO2 in the dissolved form, but with the objective of performing CCS. So this case, the first one, CO2 dissolved, is something developed at BRGM, so that we know it very well. But the idea really here is to use geothermal energy to decarbonize an industrial activity. So here we are still in sedimentary and porous reservoir, and we have the presence of an industrial emitter, so a plant, and its activity is producing CO2. So the idea is to use a really low temperature geothermal doublet, so the set of 2 wells, injection and production, which means temperature between 30 and 90 degrees C, to give you a broad range, and to store the CO2 emitted by this industrial activity in the reservoir using the geothermal doublet, and dissolving the CO2 in the water. So it's a system that is intended to be local, with no transportation of transport of CO2. The injection site really is the site where CO2 is emitted. So the depth is typically something like that, between 1 and 2 kilometers, let's say, and 60 to 80 degrees C, generally at that depth. And the energy production is typical of low temperature geothermal doublet, and the estimated CO2 that can be stored is on the order of 1 million ton CO2 over 30 years. So the important thing is that, of course, this type of concept is not adapted to big industrial CO2 emitters, but that's why the target for this concept is really small industrial emitters, emitting typically something like 100 kiloton of CO2 per year. And the index of service ratio is pretty much balanced, more balanced than others. So it's about equivalent on the potential of energy production and CO2 storage. So the next one is geothermal bioenergy CCS, so geothermal BECCS. So here, the source of CO2 is a bioenergy combustion plant, which means that the idea is to storing this CO2 is to have negative emissions. What is described in the only paper talking about this concept is that we are using both, the power plant is using both electricity, is producing electricity with bioenergy and geothermal energy. So for that, we need relatively high temperatures, which targeted is more than 160 degrees C, at relatively, so the depth seems a bit inconsistent, the depth range, but anyway, that's what we find in the paper. And the energy production is very high because we are combining bioenergy and geothermal energy, and the storage capacity is also estimated to be high, but to reach those rates, we certainly need more than 2 wells. So several doublets are needed to get those range of CO2 storage capacity. So the last one is the CCS-driven concept. So where geothermal energy is used for capture and for storage in dissolved form. So the main objective here is clearly CCS, but the idea is to use geothermal energy, geothermal heat, and also the dissolved methane, which is in the brine, to minimize the energy penalty for capture and storage. So we take benefits of these energy sources to decrease the energy demand for capture and storage. So as you can see, this requires a relatively high depth and temperature, and the energy production predicted is very high, as well as the CO2 storage capacity, but tens of wells are needed, and that's really difficult to set up, but interesting concept. So the last category is the other type of synergies between CCS and geothermal energy. So the first one is synergies through pressure management. So basically, the idea is to avoid the pressure buildup in the reservoir, because when you inject supercritical CO2, so we are here back to, so we have this type of reservoir where we are managing pressure buildup by pumping water out of the reservoir, and of course we provide some space, and we are using this water, which is at relatively high temperature, at the same time to produce geothermal heat or electricity. So this extracted water is not meant to be reinjected in the reservoir, or only partially. So so it means that it has to be managed, which probably complexify the feasibility of this concept. So you have to manage potentially great amounts of CO2, especially if you plan to store several 100 million tons of CO2 over 30 years. So you need a lot of wells, and yeah, the idea, the interest is that you can reach high CO2 storage ranges, but of course this is at the price of a relative great complexity of the system, and once again the management of the water at the surface, which is not an easy thing. The second one is synergy through dual use of the same reservoir. So so here the idea is to use the same, or to share the infrastructure, to have at the same time production of geothermal energy through hot water, and at the same time use the injection well to reinject supercritical CO2 and water. So it's co-injections, and of course the one important thing is that there should be several kilometers between the injection and the production well, so that the system could work. Because we are injecting both phases. So the temperature and the depth targeted are rather small, so which means that we will have a low energy production, but potentially a great amount of CO2 stored in the reservoir. The next one is the hybrid energy system. So here it's about integrating several of the items that were previously presented in other concepts. At the same time, the plan is to exploit geothermal energy, some fossil or ideally biomass energy, and CCS, so that near zero or negative carbon if biomass energy is the source of CO2 for producing electricity. So the carbon capture process is here optimized by using oxy-combustion, and the pressure management of the reservoir is also taken into account by removing water and partially reinjecting it in a shallower reservoir, as indicated here. It allows to some short-term and seasonal energy storage, which could be also something interesting in this concept. But here again, at the price of a relative great complexity of the infrastructure with several tens of wells. Okay, the last one is is named CCS, with geothermal energy for capture process. So here the idea is to use geothermal energy as part of the energy needed for CO2 capture, but the authors plan to use two separate reservoirs which are close to one to another, which sounds as a bit complex, but to find. I mean, but on one hand you have pure CCS storage, and on the other hand pure geothermal extraction. So two separate activities. But the idea is to use the benefit of geothermal energy to minimize the energy demand for geothermal for CO2 capture. Okay, so now let's keep to the screening methodology that we have defined. So basically, this methodology relies on both infographics and on some comparison that is possible using some criteria that we have defined. So let's have a look at the infographics. So the interest of that is to have all the concepts previously presented, and probably too quickly presented, but just to show you how they can be compared one to another. So if we have two axes with power capacity on here and storage, CO2 storage capacity, so we can define the borders of this study with our pure geothermal exploitation and CO2 storage, or a cut-fix application without use of geothermal energy, and then we can have all the different concept placed, and the black spot represent kind of the barycenter of the order of magnitude of here, for instance, we have something like 10 million ton over 30 years, and something like maybe 5 megawatts of electricity. And we have all the others again, with each of them being identified by a specific color, as you can see here, and the others. And at the end, you have all your concepts that were presented previously, plus the concept out of the scope of this study, but that are briefly described in the report. So as another way of comparing those concepts, we have this kind of thing with a scale ranging from pure carbon storage to pure geothermal energy exploitation. So you can see how each of the concept is placed on this scale. So this is something interesting to have a quick look on the capacities of each of the concepts. There's another interesting thing is to have the viewpoint for external emitters. Some of the concept need and they do not need any external emitter because they are using CO2 that is coming from geothermal energy, for instance. Some others need to rely on the presence of small emitters, and some others require large amounts of CO2 to work. So they can be classified during considering those criteria. Also, we have this sketch with an overview of research and paths to commerciality. So on the right hand is concepts that are really close or already at pilot stage and commercial operation. So as you can see, most of the concepts are on the left, which means relatively far to commerciality. And now if we look at more quantified comparison, so actually we have defined 17 key performance indicators that we have grouped into 7 categories. The idea was to provide qualitative criteria first, and then in the second time try to attempt to quantify the performance for each of these 17 criteria. Using a score between 1 and 5, 5 being the highest, being the better. A total score obtained by summing all score by per criterion is meaningless according to us, because only a weighted average could make sense. And of course, this is not neutral, and we are supposed to be neutral in this study. All the data have been included in an Excel spreadsheet, and this file is attached to the report, so I guess you can all have access to it, and you can manipulate the data and do your own classification or your own ranking according to criteria of interest, according to your own priorities. So how does it look like this this Excel file? You have columns with various concepts, and for each of the concepts you have lines, and in each line you have a criterion, a main criterion and sub-criterion. And a notation between 1 and 5 for each of the criterion, and as well as a color scale, just as indicated here. At the end, you can produce this type of tables where you can find kind of a summary of the scores for each of the KPI categories. So this is not the 17 KPI, but only the main categories, and so that you can easily have an overview and compare more in a quantitative way the performance of each of the concept. But we are aware that this is debatable, and of course we continue to play with those numbers with the Excel file. That's the main objective. Okay, so about the last question was about the potential application areas. So each concept requires the coexistence of several conditions, both geological condition for geothermal exploitation and geological condition also for CO2 storage. And second time, all of the concept needs CO2, so you need a CO2 source that is, and if the CO2 source is distant from the site, so you need a transport infrastructure. The idea basically was to produce geological maps and CO2 source or network maps and superimpose those two maps to identify the most favorable areas at various scales. Just like here, we have an example with the Clarke Atlas with in yellow the favorable geology area and some CO2 sources or power plants represented with colored dots. But the reality is unfortunately a bit more complex. So, and we have realized that this appropriate geological data and CO2 source maps are not available for every country, and generally have to be built from raw data, which takes a lot of time, and when these data are available. So, moreover, we have this criteria, geological and technical criteria alone do not guarantee the applicability of the concept. So we have to consider several other concepts that I don't have time to detail, but as you can see, just like land availability, local interest, and so on, the existence of a needing network or not, and of course the aspect related to social and political acceptance, and some legislation on and regulation on to make the things feasible, as well, of course, at the end, some business model for things to be achievable. So what did we do at the end? It was not possible to produce the specific maps we intended to do at the beginning of the study, but we have provided some exemplary case studies in the report to illustrate what could be achievable. So I know that I'm pretty late, so I'm going to skip that one. Sorry for that. You will find all this in the report, the type of maps that can be produced. And I go to the conclusion and some recommendations. So if we go back to the initial questions related to this study, so what type of hybrid CCS geothermal system are operational or described in the literature? We have found more than 150 papers describing 15 concepts as of end 2022 when the literature review was finished. And this concept falls in three main categories: use of supercritical CO2 as a heat vector, water-driven geothermal concept with CO2 reinjection in majority of the cases as being entirely dissolved in the water as well, and some other synergetic uses with lighter hybridization. So this is something that shouldn't be there, but anyway. The development level of those concepts goes from purely conceptual papers to some demonstrator and all this is highly heterogeneous between the concepts. That's what makes comparison very difficult. We have developed this set of infographics that I've showed you more in detail. And in conclusion, we can say that the hybrid use of the underground with CCS and geothermal energy in particular clearly makes sense according to us as part of the actions to be undertaken to mitigate climate change. So there are a lot of ideas of using the underground with hybrid options. So the second question was about what main criteria should be considered. It's a complex task really, because large heterogeneity between the levels of description, knowledge, feedback for some of the concept with the pilots and overall maturity of the concept. We have nevertheless proposed 17 key performance indicators that we have grouped into 7 categories. So these are the categories I'm not going to enter into detail now. The idea was to provide an overview of all this content in terms of something which is closer to performance. And for that purpose, we have produced a series of infographics. And to enable more quantitative comparison, we have all the data included in an Excel spreadsheet. And for each of the KPI, you have the possibility. We have a score, but of course this can be modified by the reader according to his or her own priority. Yes, so what we can say is that the most ambitious concept in terms of plain IEAGHG delivery and high CO2 storage potential, just like CO2 EGS, CO2 CPGES, Earth battery, or hybrid energy system, they rely on relatively high technological complexity that still needs to be proven to confirm feasibility. And they require a large amount of CO2 that should be made available at the selected site. Conversely, the lower capacity systems, such as most of the water-driven geothermal concept with CO2 reinjection, have the advantage of relying for most of them on simpler and more mature technology. So making this technical feasibility more likely to be achievable or already proven by existing demonstrator. We can cite CalFix, CLEAG, or CO2 reinjection, for instance. We need also, for this concept, a high level of replicability and deployment to have measurable environmental impact. So the last slide is about some recommendations. So we think that public bodies have to adapt the conditions and rules for their future calls for proposal on this topic, and proposed topics specifically dedicated to hybrid use of the underground. And we think that replicability potential and life cycle analysis performance should be a really key criteria to select the proposals. So we really advise that these two criteria are on the top list for the evaluators. We also recommend that regulators and policymakers adapt their regulations to facilitate the deployment of this hybrid concept, at least for the pilot phase. We also recommend that some funding is available for new subsurface data acquisition campaigns, which are really needed. But in return, those results should be made available to the whole scientific community for future projects. This should be a condition. We also recommend that governments adjust their policies to strengthen and broaden carbon pricing mechanism, which are most of the time driving the feasibility of such a project. And they need to make them more attractive to good performers and maybe more punitive for others. The scientific community, industrial company and public authorities, city, state, region, country, they have to present things in probably another way to convince the public of the absolute necessity of setting up these types of geothermal and CCS projects. So this requires close cooperation with sociologists and communication professionals when you're preparing a project. So I think I'm done, and I thank you very much for your attention and your patience because I'm pretty late. So thank you.
Thank you very much, Christophe. It's a very impressive body of work that you've put together, and I think you, as you say, you screened a lot of papers and definitely produced that dispassionate review and then brought it together in terms of the sort of critical analysis. So I definitely recommend that the audience gets hold of the report and delves in deep to all of the detail of the report. You've done a great job. I've just got one question in the question box, so if anybody else would like to make a comment or put a question in the question box, now is your time to do so. We have about 8 minutes left here for some questions. So just one question so far, which was, by whom or what company was a carb fix-like concept in New Zealand introduced? I don't know whether you remember that detail.
You want me to go? Next. Yes.
Can you just repeat the question, please, Nikki?
Sorry, yeah. So by whom and what company was the carb fix-like concept in New Zealand introduced?
Yes, I don't know. Maybe no, I don't have the answer. Maybe Annick, you have some idea of the company?
Yes, as mentioned at the bottom left of this slide, this was included in the review, and we can find more details in the report. Here, this is only a summary and mostly focused on the Icelandic context, but it was included in the work. Yes.
Yeah, do you remember who it was, Annick? I think it's probably difficult to delve into the report at the moment.
Yeah, we have to open the report, but
yes.
Faut pas regarder l'abstract, faut regarder. Ouais. We don't have the name of the company.
Yes,
maybe in the paper, maybe.
The name of the fields are Gatama, Riki, and Teuka, with Mercury, New Zealand, and the depth is around 2,500 meters. The range of temperature is between 200 and 300 degrees, and they plan to re-inject the non-condensable gases. This is indeed, from the information that we found, it was in development in last year, but we should maybe update this work. As mentioned by Christophe, we've completed the study end of last year, and so maybe there could be some new updates that will already be necessary on the work, since projects are progressing very quickly.
Yeah,
Okay.
I think, yeah, Rowena is looking at the report, and we have the name of the company, well, the operators in New Zealand. It's Mercury Energy
Yes.
and Contact Energy.
Okay.
So, yeah.
I hope that answers your question. I've had another one in from Keith Wise at the OE UK. Brilliant paper, thank you. For the maps, is the UK covered? Question mark. We possibly lack the higher temperatures available. However, all the other aspects, large opportunities highlighted. I think you did look at some data from the UK.
Yes, we have data from the UK that I didn't show yet. Yes, we have presented in the chapter on the mapping of the more favorable area. We had maps from the UK, but we didn't get to a conclusion about which area is favorable for that or that concept. So as we have discussed previously, this really is a project in itself. We need to determine that. So far we don't have any conclusion. I don't have in mind a conclusion about UK and the feasibility of that or that concept. But certainly some of the concept could be interestingly studied in some part of the UK, but this should be done after a specific study. So what I didn't say during the presentation and what I didn't show you about the maps is that producing those maps takes some time, specifically if you can have access to GIS. So geographical information system. If a geographical information system is available, it's easier and takes less time to manipulate. But yes, in Europe we have. Maybe we can show this map, but it's not dedicated to UK, but it's more for Europe. Let's see this one. Here, for instance. Oh, can you see? Yeah, so we have this map for this type of concept. For instance, we have on this map CO2 emitters, which are the black dots here, and the storage unit as identifying a CO2 stock project. So which CO2 storage area is favorable for CO2 storage, and then some sort of geothermal potential mapping, but it's not. It's only temperature distribution at 1,000 and 2,000 meters, which is not very favorable to England. So basically, what to UK in general. But I think there's probably a lack of geothermal potential in the UK for. But I'm not a geologist and I don't know UK, but Rowena probably knows better than I do. But I think, yeah, for all this concept, we need a geothermal potential, and that's could be because if you look at the map, it's not very clear, but there are some blue areas in the southern part of England here. But certainly a more detailed review would be interesting to carry out, but so far we didn't get any conclusion.
Yeah, we had to concentrate on a concept basis.
Yeah.
Yeah, you did an awful lot of work. Okay, I have got probably time for 2 more questions. Do you have any cost comparisons of the different storage technologies?
You mean a comparison on what aspect?
I think just in terms of what the costs would be for each of the technologies in terms of overall operation costs or setting up costs.
Because we have attempted to provide those some numbers to compare things between all the concepts, but of course, basically, what has to be kept in mind is that when storing CO2 as being in a supercritical form, you have the potential, you have more potential to store larger amounts of CO2 than when being dissolved in water, because being dissolved in water means that you cannot go beyond the solubility limit. So of course it limits the amount of CO2 that could be stored. So basically the concept relying on supercritical CO2 storage will provide more performance in terms of CO2 storage capacity, but at the same time they are probably more complex to manage, more complex to set up for sure, because as you have seen, most of them require to have several wells or even several tens of wells. But there are also some more leakage risks with CO2 using supercritical CO2 than dissolved CO2. So all this makes that on one hand you have something with great performance, but probably more difficult to manage and to set up, and on the other hand, something less complex to set up but less performance. So, which means that for those concepts with lower performance in terms of CCS, they really need, as it was said in conclusion, to be deployed at large scales to have an impact on the fight against climate change.
Thank you. Yes, another member has commented that there's a lot of wells involved that would negatively affect the economics, which you've said. And thank you to Rosie, who said that the New Zealand case is a Dunedin-based company, Aurora, with wells being drilled near Bluff in the South Island. I'm aware that we're at 12 o'clock, so we'll probably end there, but I'd like to thank the team at BRGM again for doing such a fantastic job on this project. It's a large piece of work to pull together. And just let you know again, remind you again that the report will be publicly available in February to be downloaded from our website, and this recording will be available on YouTube. So if you'd like to go back through it, obviously you'd be very welcome to do that. So thank you very, very much for joining us today. Good afternoon.
Thank you, Nikki, for your time and the collaboration, which was very fruitful. Yeah, we really appreciated working with you.
Very welcome.
Okay.
Thank you.
So